So we're almost to the point where we're able to actually do a full experiment or look at what a full experiment would look like, including the tree diagram. But for now, we want to talk about control, blinding, blocking, and confounding. So we've talked a little bit about control already. Obviously, we want to compare two groups or three groups or four groups. And to help with that, we use a control group. So in our control group, typically there's no treatment or whatever the common treatment is. So if typically you get, a fever and the typical response is, take 400 milligrams of Tylenol, then that would be the control group, is whatever is typical. Blinding is when we do not allow individuals to know which treatment group is being, or which treatment is being performed on them, or which group they're in. And sometimes we don't let the people who are collecting that data know that information either. So a single blind involves where one of the two, so just one of the two, doesn't know who's in which group. So maybe it's you don't know that you're in the treatment group or in the control group. If it's double blind, that means the people who are recording the data also don't know. So it could be that that information was randomly assigned and it's on a computer somewhere and nobody gets to see it until the experiment is over. Or it could be that there is a sort of an administrator that's not involved in any of the collection of data who knows who's in which group. The reason blinding is important is because of the placebo effect. So a placebo is a fake treatment that looks like the treatment being tested. So let's say we're looking at headaches and this group gets a placebo, which is a sugar pill, and this group gets 400 milligrams of Tylenol. And so I still feel like I'm getting the Tylenol because you've given me a pill and I've taken it. And just telling someone that they're being treated, in fact, can aid in recovery, and that is called the placebo effect. So sugar pills often show a 20% improvement in patients because they feel like they're getting a drug that's going to help them to feel better, and that causes them to feel better. It's like when you're a kid and your mom kissed your boo-boo. It didn't actually take away any of the pain, but you believed it would help, and so it did. And I promised we would talk a little bit more about blocking in detail, and that's what I want to talk about now. Here's a situation where I want to test the amount of juice a lemon will produce based on the temperature it is sitting in. Let's say I want to decide, I decide to study 36 lemons, and I purchased the lemons from Hy-Vee, but they only had 24. And I really wanted 36, so then I went to Baker's, which is another grocery store, to get the other 12, but those Baker's ones look a little bit different and a little bit smaller. Now, because my purpose of this test or experiment is to determine if juice levels will change based on temperature, having a smaller lemon might affect that. That might be a problem. And therefore, when I design my experiment, I'm going to have a block that has my 24 Hy-Vee lemons, and I'm going to have a block that has my 12 Baker's lemons. And when I do my experiment, I'm going to do whatever the experiment is the same for each block, but when I get to the end, I'm going to compare only the Hy-Vee lemons with the Hy-Vee lemons and only the Baker's lemons with the Baker's lemons. So again, the reason that we do this is we put them into different groups, and then within each group, then we're still going to do our randomly assigning, just like we talked about before in like any experiment. So it's kind of like stratifying in sampling. So we're just looking at two different groups and then doing the experiment for each of those groups. And what it does is it helps clarify the difference between basically the groups that we started with. It's called randomized block design, And then again, I told you I would give you an illustration of what that looks like. I sort of did on the last slide, but in the next video, when we look at the example, I'll show you what that means. First, let's talk about confounding. So let's say I taught the same course in the winter and in the spring. And in the winter, I taught in a very subdued manner. I was very tired, and so my teaching just wasn't on point. I was just, sort of boring. And in the spring, I was super excited. I was feeling better. I was just animated and enthusiastic and ready to go. And at the end of my course, I asked my students how much they learned on a scale of 1 to 5. My winter students said an average of 2.3. My spring students averaged a rating of 4.05. So, does that mean it happened because in the winter I taught in a subdued manner and in the spring I was very animated and enthusiastic? Or is it just that my students were also in a better mood because, it's spring, and spring in Nebraska, except for this spring that we're having right now, is typically amazing. So, again, was there something else at play like the weather? That is what a confounding variable would be. So a variable that would kind of like a lurking variable that we talked about before. So again, two factors are confounded if the levels of one factor are associated with the levels of another. So in the example of our teaching style and weather were confounded. The way that I taught changed based on the weather. Possibly my students' learning changed based on the weather as well. Another example, a bank sent out 50,000 low rate, no fee offers and 50,000 high rate with a fee offers. And obviously, there were many more responses for the low rate, no fee offers. But the bank doesn't know, was it the low rate that everybody loved? Was it the low fee that everybody loved? Or was it that, that it was the combination of factors? So instead, they could send out a low rate, no fee, low rate with a fee, high rate, no fee, high rate with a fee, and then see where they got the most responses.